My name is Derrick Allen, and my project consists of the optimization of a go-kart braking mechanism. This project is for MENG 4312, section 062 of System Dynamic Controls. First, I will go over the project and the scope of the project. I will then show the mechanical system, free body diagram, and such. After that, I will go into the mathematical modeling of the system and try and understand the relationship between the pedal position of the brake and the go-kart's velocity. So this project, will model and discuss the mechanics of an inexpensive go-kart brake. So go-karts range from about $300 to about up to about $10,000 if you're into professional racing or anything like that. So we will stay at the lower end of the spectrum where the brakes are rudimentary. So the mechanical system consists of a damper, which is created by the braking cable when it pulls. It has a spring which reacts to the movement or the force from the foot stepping on the pedal. In addition, it has a pivot point. And if you look right here, this is the sort of braking system that I'm modeling. And here's a simplified diagram of it. And here I went into a free body diagram of my system. Okay, so the mathematical modeling of the system consists of the equation of motion, which was derived from the actual model that we saw in the last slide. This is the basic model of the system. You have the input of a force, and then you have the damper force that reacts to the force, and you also have the spring force that reacts to it. You take the Laplace transform of this function and you get something like this out. And afterwards, you divide through by your B, which is your damper force, and you get this function. This function is the one we're going to use to create our block diagram over here. Right? As you can see, the input f of s goes in, it's multiplied by L1 over BL2. Is then added, or let's say K over B is subtracted from it. It then goes to S x of s, and then the output x of s. So basically what this will help us do is pretty much understand where the pedal is at any time t. We can take this and turn it into, or convert it back into the time domain from the Laplace domain, and we get this function here, and these are functions of time. So basically what this will allow us to do is take this time value, right, and this time value, and kind of begin to gain an understanding of what the system is doing at any time t. So once we have these time t's, we know that x dot is also equal to velocity, right? So if we set our x dot equal to 0, right, our x dot of time equal to 0, then we know exactly how long it takes for our braking mechanism to work. and we can begin to optimize our system by inputting different values and such. So basically, the ideas presented in this project are independent of any specific values. We don't have finite values to place into our system, so we are trying to optimize the overall system. If values are provided to us, then all of the features of the design can be optimized very easily by just inputting values and changing things up and understanding where things go. This system does act as a spring damper system, which means it has a damper on it, it has a spring on it, and it has something that causes a reaction from the damper and spring, some force F or some function of force function of T time that causes the spring and the damper to react. And by combining the equation of motion with the kinematic equations of motion, we can then begin to understand how the pedal distance or the position of the pedal or its distance from its original position kind of affects the velocity of the system, velocity of the go-kart. The references I used for this project was basically our System Dynamics book, the fourth edition by Ogata. So thank you so very much for listening. You have a wonderful day.